Welcome everybody to today's webinar. Our speaker is Andrea Bonfati. Andrea studied astronomy at the University of Padua in Italy and finished the master's degree in 2012. He obtained his PhD in astronomy on the topic of the ages of stars with PhD supervisor Sergio Ortolani, also at the University of Padua in Italy. And then he became a postdoctoral researcher at the University of Liège in Belgium under Michael Guillaume and Valerie van Rodel. They stayed for 4 years. And then since January 2020 now, he has been a postdoc at the IWF. And his expertise is, as you can see, related to stars and exoplanets. And today he will talk about the insights of dwarf in Gravity Valley. So thank you, Andrea.
Thank you, Ludmila, for your presentation. Thank you for coming here. I should add that I need to thank Patricio that offered me the opportunity to give in the seminar because I was not supposed to do it, but okay, I will do it. So another topic, of course, and as you may guess from the title, today we're going to talk about exoplanets around dwarfs and with a specific focus on the so-called radius and density valley. So the first question is probably, why do we care about dwarf within the exoplanet field? I would say there are pros and cons for targeting dwarfs when one is interested in detecting exoplanets. So dwarfs are among the most popular and common stars in the universe. They are characterized by low mass and small radius. And this is pretty interesting if one wants to detect exoplanets. Why? Because we basically rely on two main indirect techniques to discover exoplanets, the transit method and the radial. And if you consider the transit method, we just monitor the star, the light curve of a star, waiting for a periodic flux drop. And if we recognize that this drop is periodic, then this is likely due to a body that is periodically occulting the star. And the magnitude of the signal is proportional to the ratio of the surface of the planet divided by the surface of the star, which means the ratio between the square radii. So this means for a given planet, if the stellar radius is low, that means that the signal is amplified, is big. And a similar consideration also for the radial velocity technique. It's also an indirect technique. We may infer the presence of a gravitational body gravitationally perturbed in the star by looking at the Doppler reflex motion of the star. The magnitude of the signal also scales proportionally to the mass of the planet over the mass of the star to the power 2/3. So again, if the stellar mass is quite low, then the signal is higher. Another thing that is worth emphasizing about dwarfs is the location of the habitable zone. What we mean by habitable zone, it's a very, very huge word, even if habitable, it can be debatable, of course. So basically the definition is related to the presence of liquid water, the expected presence of liquid water on the surface, but given lots of assumptions and blah, blah, blah. But yeah, if we start on simple theory, the idea is that the location of the habitable zone in case of dwarfs, which are dim and not very hot, is quite close to the star. And the technique I mentioned before, the radial velocity and the transit method, are biased in the detection of the exoplanets that are quite close to the star. So this means essentially that when discovering planets around dwarf, basically we are likely discovering planets that are within the habitable zone. There are also some cons, let's say, when one wants to target dwarfs with the goal of discovering exoplanets. Dwarfs are characterized by strong magnetic activities, so massive coronal ejections, high energy emissions, and this plays against the possibility of the planet to retain an atmosphere. And without an atmosphere, it's probably harder to have life on those planets. And in addition, since these planets are quite close to the star and the star is not very massive, they are supposed to be, these planets, tidally locked with the star, which means that essentially they are always showing the star the same hemisphere. And therefore, we might expect huge temperature gradients between the day side and the night side. So extreme condition probably for life. It is also true that these planets around M dwarf can also be habitable despite this unfavorable stellar environment, as it is discussed like in recent year in the literature. There's, for instance, one nice theory that is presented like in ÖAW et al. 2022 that says that even if a planet around an M dwarf is beyond the habitable zone, so it's supposed to be an ice at the surface, if it has basal melting that comes from some kind of tectonic activity or heat from the inner side of the planet, it's possible that there's an underneath ocean below the icy surface. And this could be an environment where life can be hosted, also considering that this icy crust can preserve the planets from the bad high energy emission from the star. All are speculation, but in any case, the M dwarf still attracts attention in the domain of exoplanetology. And basically, with the present day seminar, I would like to give you like a broad summary of this paper that I had the pleasure to lead in 2024, which was a joint effort between the CHEOPS space-based mission and the MAROON-X spectrograph, beyond many other facilities, to properly characterize TOI 732, which is an M dwarf hosting two planets, planet B and planet C. And given the specific properties of these planets, well, they constitute a sort of starting point to then explore in the scientific discussion the so-called radius and density valley, with a specific focus on this M dwarf, because this is something that is in a way discussed in the literature, but about FG and K stars, and not very much about M dwarf. So I will try in the second part of the talk to give you some insights about what is the radius valley and what are our conclusions, our knowledge so far about the radius valley around M dwarfs. But first of all, let's start with the characterization of the system. And to characterize the system, we have to start from the star. And why that? Again, because we rely on indirect techniques to discover exoplanets. So this means that if you want to get absolute parameters for the planets, like the planet radius and the planet mass, then you need absolute parameters, first of all, for the star. So as you have understood already, TOI 732 is an M dwarf, yes. It has a radius of 0.4 solar radii. This estimate was based on SED derivation. SED stands for spectral energy distribution. Essentially, we got multi-band photometry, the total bolometric flux of the star, and if the distance is known from Gaia, you can then retrieve the bolometric luminosity, and by inverting Stefan-Boltzmann law, if the effective temperature is available, you can get the radius. And about the mass instead, we basically plug in spectroscopic parameters plus the radius into evolutionary models, and we infer a mass of 0.4 solar mass. So typical properties of an M dwarf. About the age is a little bit tricky, because there's no possibility to infer ages of M dwarfs by evolutionary models, since their evolution is very, very low on the HR diagram. So we need other techniques. Essentially, we consider the work available in the literature since 2018 by Rocha Pinto and collaborators, where essentially they provide like a probability density function that relates the UVW velocities of stars with isochronal age for a big sample of stars, the one taken from the Geneva survey. UVW are essentially the components of the velocities in the galactic frame. And we may expect some kind of relation between the velocities and the age, because, for instance, you know that stars belonging to the thin disk of the galaxy tend to be younger, while instead stars belonging to the thin disk, and then the halo can be older. And W, for instance, is the component of the velocity perpendicular to the galactic plane. So high W would scale according to greater ages, just to give you an idea. So essentially, when you collect the UVW velocity of this star, you can make some speculation in terms of probability about the age of this star. We conclude that this star should be older than 2-3 gigayears, and this was corroborated by its inactivity that we spot by analyzing the equivalent width of the H alpha in the spectrum, and also by applying some gyrochronological considerations such that we expect to have a turn-off in the rotation spin rate for ages greater than 2-3 gigayears. So This is the kind of bottom limit of lower limit that we set on the age of this star. And then about the planets. So as I mentioned before, we have two planets. Planet B, it's an ultra short period planet with a period that is less even than 1 day. So this means that it orbits the star very, very frequently. And then we have an outermost one with a period of around 12 days. This system was already studied in literature by 3 different collaborations. However, in this paper, we were able essentially to double the number of space-based transit events that were available, thanks to CHEOPS and also to the addition of the further test sectors that popped up quite recently before writing the paper. And there were also around radial velocity data available, but we, thanks to the collaboration that we put in place with the MAROON-X consortium, we were able to get also these RVs that further give much more constraint on the mass of the planets. Here you have an overview of the amount of data that I needed to deal with when analyzing everything. So essentially, we had 140 transit events of all these 2 planets that were observed over a time scale of 4 years. And here on the left-hand side, I list all the facilities that were from where the data were taken. I highlighted in red specifically the new addition that were made specifically in this paper with respect to what was already available in the literature. So you can see CHEOPS and TESS essentially, and then the Muscat 2 facility that enables you to observe in different filters, the LCO network, TRAPPIST North, the MERF project, so lots of facilities. So 140 transit events on an average. And then about the radial velocities, we got 165 radial velocity data points. So as already mentioned before, there were already radial velocity data available in the literature, specifically the more precise one comes from Alps and Alps North, slightly less precise from Carmenes, even if it's suited given it's set up to observe M dwarfs. And then we added here, highlighted in red, the data coming from MAROON-X. And MAROON-X have 2 different channels, the blue and the red one, with the red one that is specifically suited to observe the M dwarfs. So the idea was take all this data, combine them together, and provide some results. And this was the beginning. So I'm quite an expert now, I would say, in analyzing CHEOPS lightcurve, but when I saw this lightcurve, I was a bit confused. So essentially, when you get CHEOPS lightcurve, and this is a typical example of a lightcurve, so the normalized flux plotted against the time, you see, okay, a pattern that in principle should show some drop where the planet should be. Actually, here it's very, very hard to see any kind of drops. So first of all, one may wonder why we have these gaps in the data. And the reason is that the CHEOPS is a low Earth orbiting satellite. So this means that from time to time, the observation is switched off. And this is due to an increased amount of the zodiacal light that is scattered in the aperture. And so this downgrade the performance of the instrument. From time to time, it passes above the so-called South Atlantic anomaly, which is an anomaly where the magnetic field of the Earth is pretty intense, and it's better to switch off the instrumentation to avoid damages. And from time to time, the line of sight intercepts the Earth limb. So that's why we have gaps. We define the so-called efficiency of the visit as the ratio between the time that was actually spent on the target over the total amount of duration of the visit. So here in this case, the visit is not very efficient either, but okay, this is what it is. Apart from the gaps, one may wonder why we have these results that is not in line, in principle, with what one would expect with the space-based mission. If you want, I give you some seconds to infer where the planets are, because it's funny, because here you should see both 2 planets, okay, not even one. Okay? So you can think about where these 2 planets are. One planet, probably you may guess, the other, I would say, it's impossible. And then I will say it's one. So what is the main reason for getting this lightcurve that is affected by these systematics? And I would say that the answer is called the roll angle. So essentially, here you have a snapshot of CHEOPS, that is a sort of washing machine that is orbiting around the Earth. And its setup is nadir locked. This means that the bottom of the telescope is always pointing towards the Earth, and there's a reason for that because we need to downlink data, and so it's good that the bottom part of the telescope is always pointing the same direction. In order to keep this kind of configuration, then from an engineeristic point of view, the telescope needs to rotate along the x-axis, along the line of sight. So this means that this produces a rotation in the field of view while CHEOPS is observing. And the rotation along the line of sight produces, okay, the roll angle, okay? Here on the right-hand side, you can see a simulated field of view around a star that was published in a previous paper of myself, where essentially the target star was removed, it was replaced by this X cross, and all these pseudo-pyramidal shapes are essentially the PSF of the stars that are in the background, in the field. The PSF is a point spread function, so the shape of the star on the focal plane, and as you can see, I mean, it's a pseudo-pyramidal shape. It's not a circular shape. It's not a regular shape. This is because of the design of the optics of the telescope. So now, the red circle is the field of view for the default aperture. If you imagine the field to rotate about the X cross, given the irregular shape of the stars, there are stars entering in and out the aperture, and they produce a spurious flux. And this amount of spurious flux is variable and depends and correlates with the roll angle, it correlates with the rotation. So you may expect that the roll angle introduces some spurious flux variable along the CHEOPS when CHEOPS is rotating. And this is essentially the modeling of the roll angle pattern. Basically, you can see the normalized flux versus the roll angle, and you can see, so if there was no systematics, basically you would expect a flat line, okay? So if you remove back, applying this model, the contribution of the spurious flux coming from the stars belonging to the field of view in the light curve, then you would obtain a nicer result. So now if you're ready, no, yes. Ta-da. So you basically apply the mathematical function there, back in the light curve that I showed you before, and then you obtain this one, okay? Where I highlighted in red the position, the location where the transit events are. So essentially, if you come back, this is the second to last orbit, where essentially, if you have a trained eye, you could see that this orbit is slightly a little bit below the others, but it was pretty impossible to guess the position of the other planet. And this is just because we got just the egress phase, so the very, very last part of the transit events. So when one see this picture, say, okay, now I can start actually. Yes, I can make a few considerations about that. So this is TOI 732c, so the outermost planet. Given the gap, we were not able to trace all the transit shape, but still we got like the central part of the transit, so we got an idea of the transit depth, even if the ingress and the egress phase are quite important to constrain the impact parameters and other planet parameters. Instead, here in case of the innermost planet, we just got the egress phase. So this, in principle, one can say, okay, we can try barely to constrain the impact parameters, even if it's really, really hard because we just. But the lesson to learn here is that, especially if you have a light curve with lots of gaps, you are forced to take more CHEOPS observations and stack one to the other in order to fill in the complete phase and actually model the transit shape. And moreover, if you deal with the ultra short period planet, like this is the case of planet B, well, if the planet is an ultra short period one, also the transit duration is expected to be short. So it may happen you are unlucky enough that all the transit event is within the gap. So especially for ultra short period planet, you need to take lots of CHEOPS visit in order then to being able to retrieve and to build the transit shape. And then, okay, once I clarified that, basically the idea was to, okay, the trend in the CHEOPS, pre-trending the CHEOPS light curve against the roll angle. Then put all the light curves coming from the facilities I mentioned before and all the radial velocities, again, from all the spectrograph I mentioned before, into a very giant code called the MCMC that they developed together with Michael Gion in 2020, where essentially the goal is to get the system parameter of the exoplanet while analyzing and trending all the data within an MCMC fashion. And when everything is done, and it took quite a while because the bunch of data were just insane, you get like this kind of results. These are the phase-folded lightcurves for planet B and planet C as coming from the TESS instrument. So you can see the normalized light curve as a function of time centered on the transit events, and phase folding means that all the transit events were stacked one to the other. The blue data points are the original photometric data, but after the defriending. The black points are the binned photometric data to guide the eye and see actually the layout of the points. And then the red line is the theoretical transit model that is expected, that was computed for the different planets. And in the bottom part, you can see the residuals, which means the difference between what was observed and what was actually computed theoretically. If the residuals have some kind of Gaussian distribution, this means that all the systematics were properly removed. Left-hand side planet B, right-hand side planet C. This is the case for TESS, and this is the analogous plot for CHEOPS. As you may notice, is that the crowdiness of data points in case of TESS is a lot for planet B, and this is a consequence of the shorter orbital period of the planet, because for TESS we had 3 TESS sectors. Each orbital period was 0.77 days. So in each TESS sector, you may expect like 30 plus transit events. And if you stack everything, you have a bunch of data points. It's not the case of planet C, which is a longer period planet. What I would like that you focus your attention in these 2 slides are the specific radii of these planets. So planet B has a radius of 1.3 Earth radii, and planet C 2.4 Earth radii. And this is going to be important during the discussion of the second part of our talk, but that is related to the radius value. Okay. And what about instead the mass? So these are the radial velocities phase folded time series. So phase folded according to the period of planet B on the left and planet C on the right, where the different colors of the markers represent the different instruments from which the measurements were taken. So we talk about the planet B with a mass of 2.5 Earth masses, and planet C having a mass of around 8 Earth masses. What is worth to emphasize is the precision we were able to get by combining all this bunch of data together, okay? So not just because we are better than the others, just because we have much more data in our hands. So I just summarized here in this table the uncertainties that were got by previous collaborations, like Cloutier, Novak et al. And Luc and Payet in 2022. And then the last column is our work. So essentially, the uncertainty on the orbital period is way less than 1 second for planet B and around 1 second for planet C. About the relative uncertainty on the transit depth, we have around 4%, and the relative uncertainty on the RV semi-amplitude, indicated with K, is 6% for planet B and 4% for planet C. And in general, we were able to drop the uncertainties by a factor of 1.6 for planet B and 2.4 for planet C. And with this remarkable precision, we were able to compute the mean planetary density at a precision level of 15%, which is quite impressive, because only 20% of the currently known exoplanets around M-dwarf are known with a comparable or even a better precision. And if you know the mean planet density quite well, then you can start speculating about the planet composition. And actually, this following slide goes along this way, because the first step to understand which can be the composition of the planet is to put the planets on the so-called mass radius diagram. So a plot where the y-axis you can see the radius, on the x-axis you can see the mass. The different data points you can see here all are exoplanets belonging to M-dwarf that were characterized with a very, very high precision density, so a density that is more precise than the 3 sigma level. And together with all these planets, I put and highlighted via stellar markers, TOI 732b here below in yellow, and TOI 732c there up there. The markers are color-coded according to the equilibrium temperature, as it is depicted here in the color bars. And to guide the eye, I superimpose on this plot some theoretical models that tell something about the composition of the exoplanet. In the upper part, you can see the blue, light blue, and purple lines that essentially are planets that are half rocky and half made of steam water or condensed water, or probably silicates surrounded by a layer of volatiles like hydrogen and helium. While instead the bottom part with the orange, brownish, and then the very bottom black line is characteristic of planets that are like Earth-like or partially silicates, partially iron, and so on. The plot is further distinguishes between models according to the equilibrium temperature of the planet. So the solid lines are characteristics of equilibrium temperature of 900 Kelvin. So this is the equilibrium temperature of planet B, while instead the dashed line of 360 Kelvin for planet C. This makes a difference in case of models where you have also volatiles. In case of pure rocky body, there's no essential difference in this regard. So what we can conclude just by looking here is that is pretty certain that the innermost planet, planet B, is basically a rocky one. Okay, if you compare this with the location of the models, and we shall call it like a super Earth. While instead the planet C, we may have a degeneracy if we just look at this plot, because it is a sub-Neptune, so it has a dimension that is still lower than the Neptune radius, which is around 4 Earth radii and 17 Earth masses. So this is like half in mass and half in radius, so a sub-Neptune. It may be richer in volatiles, and so it may be like a rocky planet surrounded by a nitrogen and helium envelope atmosphere, or a steam world, so rocks inside in the core, and then water in the steam condensed state, also condensed state all around. So now that I show you the characterization of the exoplanets, I would like to talk instead of, in this second part, of the so-called radius valley. So what is this radius valley, and why this system represent a sort of starting point to then study this kind of feature. So this concept of radius valley was first introduced by Fulton and collaborators 2017, who focused their attention on FG and K stars. Here you can see a plot that essentially show the radius distribution of exoplanets orbiting these stars and having orbital period less than 100 days. And it's pretty clear that this distribution is bimodal. So you have a peak at around 1.3 Earth radii, and another peak at around 2.4, 2.5 Earth radii. And so if you remember correctly, these are exactly the size of the planets in our system. So it's very interesting to note that our two planets straddle the radius valley from one part and the other. This, of course, was a work based on FGK stars, and then we will get a little bit more details also about what happens in N4. But in any case, to complete the discussion, so, okay, there are two peaks. So the following question is why there are two peaks, why there is this valley, what physical phenomena can cause this drop? Because essentially, yes, we see a paucity in the size of planets in the range between 1.5 and 2 Earth radii. One of the explanations that was given at that time was that essentially planets formed as rocky quartz whose size may amount up to 1.5 Earth radii, and then they may also acquire and collect an envelope all around that makes them puffier. So essentially, the first peak is the characteristic of bare rocky cores, while the other peak is instead typical of planets that are characterized by an envelope all around. And why then the drop? Because in terms of atmospheric evolution, one may speculate that passing time, essentially, the planet surrounded by atmosphere may lose it. The atmosphere can be stripped away because of the high energy emission coming from the star. This is the so-called photoevaporation phenomenon, or because of the so-called core power mass loss. So essentially, heating coming from inside the planet that release energy and throw away the atmosphere. These two are the so-called thermally driven mechanism. There's also another possibilities in some cases, some impact erosion, so catastrophic events of collisions with other bodies that release lots of energy so that the atmospheres run away. Or another possibility again is mostly instead related to the formation. If the planet is formed in a gas-poor environment, then it has not the possibility to accrete the envelope, and so its size may last up to 1.5 Earth radii. But then, okay, since 2017, the study advanced, and specifically the community was interested in making the previous plot, which is just 1D, so just the radius distribution, in a two-dimensional plot, so where the radius is plotted against the orbital period to check if there are some kind of features we may expect. And actually, there are different works from a pure theoretical perspective that tend to quantify the slope of the radius valley that is expected as a function of the orbital period. And so we have, in general, negative slope on this plane, passing from steeper values where the pure photoevaporation is at play. And here in this table with photoevaporation, we mean, given the work by Owen and Wu, something that was computed like according to the energy limited formula, so a very simple model. Then coming to a milder slope, minus 0.10, if all the thermally driven mass loss mechanisms are taken into account, so not only photoevaporation, but also core power mass loss. And in addition, in that paper by Holter et al., also a more sophisticated hydrodynamic simulation was performed. And then we reach the bottom part of the table, where instead we expect a positive slope in the valley in case of a pure gas empty formation. Well, in case of a pure gas empty formation, there wouldn't be neither a valley, because if there's a pure gas empty formation, only bare rocky cores can form. And so basically this plus 11, so this 0.11, this slope is just the upper part that the bare rocky core can reach as a function of the orbital period. There was a work in 2023, among others, that focused its attention on FG and K stars by Owen by Nellen. And here it plotted the radius versus the orbital period. Actually, it found a negative slope in the valley. Here you can see a paucity of planets. The green markers are essentially the sub-Neptunes, and the light blue markers are the super-Earth. The black line here in the middle of the valley is actually the best fit line. The shaded area is the 1 sigma uncertainty, and these dashed lines are like the cliff of the valley. The authors found a slope of minus 0.11, which is in line with thermally driven mass loss events. So from these results, they speculate that essentially the radius valley around FG and K stars may be caused by thermally driven phenomena, so photoevaporation and core power mass loss. But in the same paper, they also pointed out that there's a dependence of the radius valley as a function of the stellar mass, as you can see here. And as I told you before, since they focus on FG and K stars, the lower limit for the mass is around 0.7 solar masses. So the M dwarfs were completely neglected. So the following question would have been, okay, and so since we expect this kind of trend, what about M dwarf exoplanets? Is there some differences that is expected in that specific category? So that's why I decided in my paper to further focus on this. This is, again, a plot of the radius against the orbital period, where I put in all the exoplanets orbiting M dwarfs that were characterized with a pretty high precision, the same as you see in the mass radius diagram before. Then, following Go and Van Allen, I applied a mixture Gaussian algorithm to cluster the data points into two subgroups. And the result is given by the two different colors, where the blue one are the sub-Neptunes and the green ones are the super-Earth. And then I applied a support vector machine algorithm that is based that is available in the sklearn Python package in order to establish the best fit line separating these two clusters of data points. I then bootstrapped 10,000 times the planet location in order to retrieve the 1 sigma uncertainty of the best fit line. And I also represented the cliff of the valley via the dashed gray lines following Go and Van Allen 2023. And in addition to guide the eye, so I highlighted with the red stars our two friends, so TI732b down here and C up there. And I also represented the two slopes that are available from theory and that describes two different phenomena. So the minus 0.10 as inferred from thermally driven mass loss mechanism, and instead the positive slope, the dashed red line, plus 0.11, which set up, as I say, the upper limit for bare rocky cores. And the equation of the line that was inferred is here below, with a specific focus on the slope that is minus 0.065. And given the uncertainties, we may see that this slope differs almost by a factor of 2 with respect to the slope that was derived in case of F, G, and K stars. And in addition, there's also tension at around the 2 sigma level. Maybe not dramatic, but still probably quite a difference. So the idea is that it's likely that the formation and the evolution mechanism that characterize planets around M dwarf can slightly differ from the one that characterize F, G, and K stars. Last consideration, looking at this plot, you can see that inside the radius valley, we call it radius valley, but actually it looks a little bit filled in, right? There's not the possibility actually to pretty disentangle the two groups. So I just hope that the Python package was doing its work properly, but actually by eye, yes, you can see maybe a paucity of data points, but maybe not that clear. And I will come also to this point a little bit later on. If we want to summarize the possible explanations that we may give to the slope of the radius valley we found, minus 0.65, well, the first explanation could be, okay, the slope that we found is like in between the one that is characteristics of the thermally driven mechanism and the one that is typical of gas empty formation, maybe with the preference towards thermally driven mechanism, but still a little bit in between. This means that if we compare our slope with the result coming from F, G, and K stars, we may infer that there's a stronger impact of gas poor formations in M dwarf systems. This was like an hypothesis already pointed out by Cloutier et al. 2021. And actually, there is also the very, very recent paper by Tom that is inside the CHEOPS collaboration, published in Science a few days ago, that actually analyzed an M dwarf system and noticed that the outermost planet is completely without an envelope, even if the innermost planet have an atmospheric envelope. And so this is the idea that probably this last planet was formed a little bit later on and in a gas-empty environment. So gas-poor, gas-empty environment could be much more common in M dwarf rather than other kind of stars. But then there is also a second explanation that is much more related to formation and migration. Essentially, according to a work by Luc and Payet 2022 that was published in Science, probably, yeah, or Nature, don't remember. The sub-Neptunes, so all these planets having a radii between 2.5 and 4 Earth radii, are not only rocky planets that are made of rocks and water layered. And according to dynamic simulation, it turns out that the steam world, which by definition can form only outside the snow line, tends to migrate inward if they orbit M dwarf. And so the fact that the slope we found here is like milder than the one that was found like around FG and K stars can be explained thinking of a partial filling of the radius gap. Because if I come back to the previous slide here, essentially the sub-Neptunes are the blue data points. If among these blue data points there are steam worlds expected to have migrated inwards, essentially you can think that at the beginning these data points were like shifted like on the right, but during the migration they shifted on the left. And if you shift like these data points rigidly on the left, basically you go filling the radius valley. So this means that essentially the slope that you might infer from a mathematical point of view is just shallower because there's not a real definition of the boundaries. Here on the left-hand side, I summarize the work that I just mentioned about 2022. They actually started talking rather than a radius valley of a density valley. What they found was that if they make a distribution of the radius size or the planet size of planets around and dwarfs, they could like distinguish three different categories. And so the rocky planets with the brownish bar, the steam world, water world with the light blue bars, and the pathy with the indigo bars. But here actually a valley is not really seen, okay? As I emphasized before also in the previous plot, it's not really clearly seen. But rather, if you realize, if you build the same histogram in the density plane, then actually there's a much more differentiation between the sub-Neptunes, either with an hydrogen helium envelope or a steam world, and the rocky planets. And so, like following this work, I say, okay, so just take the planets I have in my sample, and let's build a plot where the planet density is plotted against the orbital period. Also, Rafa, so Luca and Payet 2022 did this kind of work, but the sample of my paper had 30% planets more. So the statistical result we could reach was more robust just because of more data in our hands. And then these are again the same planets that you saw in the previous slides. Now the super Earth are above just because they are characterized by higher density, and the sub-Neptunes are here below. The red stars are again our TOI 732b and c. And if you follow the same mathematical steps as before, the best fit line that divides the density valley, which I would say here is much clearer, is compatible with a slope equal to 0, so an horizontal line. These are the same results that also Luca and Payet found in their papers. And so the interpretation that among the sub-Neptunes, there are steam world, the steam world, especially around M dwarfs, tend to migrate inward, and then the radius valley is partly cancelled, while the density valley keeps being there, is something to be taken into account. Probably the scenario next one, we still have probably to think about the complete setup of this exoplanet system. But yeah, essentially this is the idea. So a mixture between photoevaporation and inward migration. So this is my last slide. Here I would say there's like a nice summary of the take-home message, like with this picture taken from Byrne et al. 2024. Who again discussed the radius valley around essentially FG and K dwarf. So where you like in the bottom part the super Earth, in the upper part sub-Neptunes, either with the steam water or hydrogen helium envelope. And yeah, that's it, and I hope you enjoyed this journey.
Excellent. Very, very much on time. Thank you. So, questions? First, Milka.
So when you do the density valley, do you redo the clustering, or do you take the clustering from your radius sample clustering?
Let me think. I redid the clustering because in order to estimate. Let me think. Yes, because I did it a few times ago. I think I redid the clustering. Yes, I think, yes. And yes, yeah.
Do the samples, do you remember if the samples were the same?
No, they were pretty consistent. I can say that maybe there was a difference like of a couple of ones like falling just within the filling, because as you can see here in the radius case, there's this partial filling. But apart from a few examples, they were kind of consistent. Yeah.
You alluded to the need for stellar parameters. So how did you determine the effective temperature then? Because this was what was missing, basically.
Yeah, I just mentioned yes already. So it's not exactly my expertise, but essentially the effective temperature, the metallicity of the star is determined using spectral analysis. So you analyze the spectrum. There are different techniques to do that. So either you can do the synthesis. So this means you compare with template spectrum, or you consider like the ionization line of the iron, and these you can relate with the effective temperature metallicity. I'm not a super expert, but essentially there's a part that comes before me within the TS3 that does that, and then I just take the parameters.
Yeah, but it means you have high resolution spectroscopy for the effective temperature, but then you use the spectral energy distribution for, the people use the spectral energy distribution for the radius.
Exactly, because from that you can guess the bolometric luminosity once also you couple Gaia parallax. So basically you take effective temperature from the spectrum and the bolometric luminosity is inferred from multiband photometry and the parallax. And when you combine together, you get the radius.
Has there been a comparison between the high resolution spectra should somehow be in the SED, right? So has this been tried? I honestly don't know.
I don't know actually. No, I don't know how to reply to that.
That's fine. I can check if I meet the people.
I have a couple of questions, but so I guess the parameter of the star are inside your MCMC retriever, right? So you need to feed them in. How sensitive it is to the mass of the star, because the error bar you have from the stellar evolution is like 1% or something. Is it really the case that we have a stellar model which can predict the mass of a star at 1%, whatever scenario?
No. So the idea is that here, since you are dealing with M dwarfs, the stellar parameters are kind of constrained because in terms of the mass, because since the evolution is very, very low, and basically you cannot expect a very, very much variation in the terms of the stellar mass. If you go to other spectral types, earlier spectral type like solar stars, then a reasonable uncertainty on the stellar mass in terms of systematics is around 4%. And so if you sum up everything together, like 5% is something that you may expect for a solar-like star. In case of them dwarfs, so they're like trickier in the sense that, so in the case of age, you cannot say anything from stellar model, like evolutionary model. In case of the mass, basically you are pretty sure about the mass because since it is an M dwarf, the mass cannot vary a lot. There's like still a tension in the model when exploring the very, very lower part of the main sequence, because there were some tension if you compare what comes out from open clusters, so the observation, and what comes out from models like in the lower part of the main sequence. The idea is that we are not really able to model very, very low mass stars. And for instance, the models I'm using, the ones from Padova, adopt like an empirical correction to match the result of open clusters. So they model it according to theory, let's say, and then in the bottom part, they make like a shift in order to match the typical trend of open cluster in the lower part of the data.
And if I can, a second question. You had this mass over radius plot where you had different composition of planets in regard. And I just was surprised, like you have 100% silicate and 90% silicate, and there's a huge difference. So only 1% atmosphere makes a huge difference in this.
Well, you have to count that this is only 1% hydrogen and helium, but in terms of the size, it means a planet that has a double size. This is the real difference. So in terms of the mass, it seems like tenuous, but in terms of the size, the planet is like way puffier because the size is double as the one would have without this envelope. So this makes actually, yes, a difference.
But if it's so sensitive to this parameter, I mean, you can have 0.1, 0.2%, any curve can be fitting there, right? You don't really know whatever atmosphere could make, okay.
Yeah, you're right. I mean, this was just the very first step towards the characterization. This plot is characterized by lots of degeneracies, so it's just to get a rough idea. So, like, if you are below here, you are pretty sure. If you are up there, not really sure. Like, more sophisticated models need to be run, and when we run the more sophisticated model, still the posterior we get almost resemble the priors. So this means that we are not really able, even if we sell the message that if you hit like the 15-20% uncertainty on the density, you can do a lot of science. But really, if you then launch the model, like being really sure about the composition of the exoplanet in the sub-Neptune regime is quite difficult. And that's why there's still this debate about sub-Neptunes. Are they made of this hydrogen and helium envelope or steam water? I mean, it's not really clear.
But if you take Earth, out of curiosity, what is the percentage of nitrogen in the atmosphere in terms of mass compared to the mass of Earth? Does someone?
When developing these models, like the Earth flag that is written there, I know that is developed considering like 67.5% of silicate and 32.5% of iron. So the amount of the envelope is almost neglected, or at least is it's 0.something%.
Less than 1 per mil.
Yeah.
Yeah, my point is if you take the purple line here and you do 0.01% hydrogen, you still will be probably above the orange line quite a lot. I mean, I don't know how linear it is,
yes, but probably yes.
Even small atmosphere here will fit some stuff in the
some stuff, yes. So then I cannot say like now on the fly where the line.
Sure. Okay, thanks.
The bottom line here is it's an atmosphere made of light elements, right? And this is linking to the formation. So is it really hydrogen, or is it water, or is it something even heavier? But here the emphasis is, okay, there is some sort of a lot of rocky stuff, 99%, and then a very light atmosphere which extend dramatically. So this is the philosophy behind this. And yeah, there is room for argument, but not much actually.
Yeah, but we're saying that the bottom line, the orange is fully stone, whatever. A bit of atmosphere could also be at the same line, essentially.
We can discuss this later. There's also another question behind you then. No? Okay. I mean, you're right. There's a lot of the genres in there, but maybe that's for later date. More questions? Maybe I have a question. Maybe that's also kind of like just a direction what Gabrielle is questioning. Because the problem is that the thing is like, okay, fine, you can put in principle an atmosphere on this, but the question is like, is it stable? Because as you know, if you have a surface gravity of Earth or 2 times Earth, you tend to lose hydrogen. I mean, that's the whole point of mass loss, right? So where is atmospheric erosion, the mass loss in this picture? Is it taken into account, or can you even take into account the frequency around dwarfs because you don't have deformation of XUV plugs, or what's your idea? Yeah.
So to take into account the atmospheric evolution, okay? Yeah. So in principle, the code was developed here by Daria, and then I further developed. It's in charge of estimating from a purely theoretical point of view the amount of atmospheric loss if you provide the code with some stellar parameters that relate like the rotation period of the star with the activity level and then the high energy flux. It was not done for this system. And I think because the problem was that probably the stellar evolution models were just set up for solar metallicity and solar-like stars. So when you go to dwarf, it's not actually easy to model them. Yeah. I
mean, that would help obviously, because then you can maybe discuss some of these with very small because they are just not stable.
This has nothing to do with the evolutionary model. This is basically very simple. It's a spherical, symmetric bone with a bit of added something.
Yeah. The evolution does not come into play here in this specific project.
Good. And I would say with this we stop our webinar today. We thank again our speaker.